So to kick off this review part 2, we're going to look at transformations of quadratic equations. And so we're going to look at what it means to vertically and horizontally transform these quadratic functions first. When we're talking about vertical transformations, we're talking about changes in the y-coordinate specifically, and it's the points on that parabola on the graph. So for example, your vertical transformations will determine whether your graph gets stretched or compressed vertically, or whether it's going to shift up or down. And then you have horizontal transformations. Now, these won't be explored too much in this course, but in later courses they will be. So when we're talking about anything that gets compressed or stretched horizontally, or in this case, what stretches or compresses the x-coordinates. And it's not the points themselves that are being stretched and compressed, but as a result of how they change, your function ends up getting stretched or compressed horizontally. And so if I look at the image over here, I can see that the original graph, which is y equals x squared, we would call that the parent graph. That is before any kind of transformation. Now, when I look at the graph in red, it has been stretched horizontally, so it is wider. But then if I look at the graph in green or aqua, it has been horizontally compressed, so it is skinnier. And of course, these transformations pertain to horizontal only because they're within the bracket. Now, diving into vertical stretches and compressions. So our general transformation algorithm is f at x is equal to a bracket x minus h squared plus k, and this should really remind you a lot of the vertex of the parabola. The variable a is what tells us whether the graph will vertically stretch or compress. When the absolute value of a is greater than 1, then we say that the parabola stretches or becomes narrower or taller. Actually, I would say narrower and taller. If a is between 0 and 1, so it is a decimal or a fraction, then your parabola is going to compress vertically, so it'll get vertically smaller, but if we're thinking horizontally, it'll by default become wider. But we're really just focusing in on the vertical component. And if a is less than 0, so if it's a negative, the parabola opens downward, but that also means that it reflects over the x-axis, so it'll be flipped upside down. So for example, if we think about f at x is equal to 3x squared, well, that 3 beside the x, that would represent the a value since it's outside a bracket. And that would mean that the graph is vertically stretched by a factor of 3. But by the same understanding, if we have the function f at x is equal to half x squared, then that would mean your graph is vertically compressed by a factor of 1 over 2. Now we have translations as well, which means that your graph won't get stretched or compressed vertically, but it'll move up and down along the y-axis. Again, pertaining to the general transformation algorithm, ax minus h squared plus k, the k is what's going to decide whether the graph goes up or down. When the k is greater than 0, your parabola is going to shift up by however many units that is. When the k is less than 0, your parabola is going to shift down by whatever value of k that is. So for example, if I look at the function f at x is equal to x squared plus 3. Well, because the 3, which would be k, is positive, and how do I know that the 3 is a k and not an h? Well, the k is always outside a bracket. So if there's no brackets around those values, then that's a k value. And because it's positive, it tells us that it moves up by 3. With the same understanding, if we look at the next example here, f at x is equal to x squared minus 5. Well, again, since it's a negative, then your graph is going to move down by 5 units below the axis of 0. So now we're thinking about translations, not growing in size, but shifting from left to right. So again, all of this information is going to come from the general transformation algorithm, which is f at x is equal to a x minus h squared plus k. Now the value of h, so the value that's inside the bracket, is what's going to control the horizontal movement. If your h is greater than 0, then the parabola is going to shift right by whatever many units that h represents. If your h is smaller than 0, then your graph is going to shift left by those amount of units. Now, what I want you to keep in mind here is that, remember, we set all things inside the bracket to 0. So that means that you take the opposite sign. So if h is positive inside the bracket, then when I'm looking at the actual value of h, it's going to be negative. And if h is negative inside the bracket, then when I'm looking at the actual value of h, it's going to be positive. So remember, always flip the sign before you decide whether it's shifting left or right. So for example here, if I look at f at x is equal to x minus 4, this here is going to, and that's squared, this is going to move the function right by 4 units. Now, how do I know that that's an h value? Well, remember, unlike the k, it's going to be inside the bracket. And like I mentioned before, we always take the opposite sign of whatever is inside the bracket to get the actual value of h. So because it says minus 4, because that bracket is set to 0, we know that this is really h equals plus 4, so it's going to the right by 4 units. If I take a look at another example where I have f at x is equal to x plus 3 squared, this will move the parent function left by 3 units because, again, that bracket is set to 0, and so the plus 3 really means that h is negative 3, so it shifts left. So now we're going to put this all together and combine all the 4 main transformations in this example. So let's say I want to look at this function f at x is equal to negative 2 x plus 1 squared minus 3. Okay, and we're going to describe what is happening with these transformations. So the negative 2 tells us 2 things. The negative tells us that there's a reflection over the x-axis, so that means it opens downward. And the absolute value of 2, the fact that it's not a fraction, tells us that it stretches vertically by a factor of 2. Now, that negative 1, which I know it says plus 1, but remember we set that bracket to 0. That negative 1 tells us that it shifts the graph left by 1 unit. So now we got this graph that opens downwards, is stretched vertically by a factor of 2, and it shifts left by 1 unit. Now we're going to talk about that minus 3 outside the bracket, which is the k value. Now if the k is less than 0, in this case negative 3, that means it shifts down by 3 units. So from the original parent function, we have this graph that is getting flipped over the x-axis or reflected, stretched vertically by a factor of 2, shift left, and shifted down. So if we're putting this all together and we want to apply these transformations to the original graph of y equals x squared, I want you to pause the video for a minute and think about how that would go. Roughly sketch this graph out and then unpause it and see if you got it right. Okay, so using the graphing calculator here, your comparison should look something like this. So in red, we have the original y equals x squared, which is all at the center of origin. And then we have the transform function. We could see that in blue, it indeed has flipped over the x-axis. So now it opens downward instead of opening up. If you look at the vertex, okay, that point at the maximum value in blue, it has indeed shifted over from 0 to 1. And then it's also been shifted 3 units down. So the vertex is at negative 1 and negative 3. And so we can see, just by applying these transformations, how the graph in red was changed into or transformed into the graph in blue. For the second part of this review, we're going to look at the domain and range of quadratic functions. So remember that for the domain of a function, it's the set of all possible x values. And for any quadratic functions, because whether they're opening up or opening down, all the quadratic functions, if I zoom in on this one here, they all go in both directions, meaning negative and positive. And I admit they kind of inch their way towards both directions, but they all go in both directions consistently and forever. So what we say is for the domain, and it doesn't matter whether it opens up or down, is that the domain of a quadratic is any real numbers. So in interval notation, we say it's from negative infinity to positive infinity. And in set builder notation, we say for all values of x such that x is all real numbers. It just means that we recognize that it goes forever in the negative direction and forever in the positive direction. But for all quadratic functions, you just write XER in set builder notation. Now, I do want to comment on something about the brackets here. If you notice, we wrote round brackets in interval notation, and that's because infinities are always non-included values. So domains of quadratic functions are the easiest to find. They're always going to be from negative infinity to positive infinity. Now, when it comes to finding the range of quadratic functions, that's where it's going to be a little different because not all values of y are possible. Now, the range really depends on whether the parabola opens upward or downward. So what we're essentially looking for is the vertex. For upward opening parabolas, where your a is positive, the range starts at the vertex y value and goes to positive infinity. So essentially, if your graph has a minimum, then you state that minimum and then you lead it to positive infinity. If the graph has a downward opening parabola, so if a is less than 0, so if it's negative, then it goes towards negative infinity. So your maximum, right, the highest possible value in your function from that maximum goes towards negative infinity. The key step is that you have to get your function into vertex form. And the h and the k is going to tell you where the minimum and maximum values actually are. So where the graph starts, vertically anyway. So let's say for the following function here, f at x is equal to 2x minus 3 squared plus 1. It's already in vertex form. We want to write the range. And we want to write it in both interval and set builder notation. Well, we can see here that the graph has a vertex of -3 and 1. Now for the domain, it's all real numbers, so there's no reason to state it here. But for the range, it has a minimum value of 1. Now I said minimum because if you look at the positive value here of 2, which is the a value, that means that the graph opens up. So this graph, opening upwards at the vertex of 3 and 1, will start at 1 and then head towards positive infinity. Now, when we're writing in interval notation, it starts at 1 and then ends up at positive infinity. Because 1 would be an actual point on the graph, we're going to put square brackets around the 1. Now, infinity is not an actual value on the graph, or it's a non-included value, so we use round brackets. So the range in interval notation is square brackets 1, comma, and then to positive infinity. Now, in set builder notation, we say that for all real values of y, such that y is going to be greater than or equal to 1. And the reason why we say it's greater than or equal to is because, remember, 1 is an actual value on this parabola. So we have to indicate that in set builder notation. Let's say we're looking at our second example here. G at x is equal to negative x plus 2 squared plus 5. So again, this is already in vertex form. We know that the vertex is at -2 and 5. Now, because of the negative a value, right, the negative outside the bracket, that tells us that it opens downwards. And because it opens downwards, that k value, the plus 5, is going to be a maximum value. And with all maximum values, we know that your graph is going to approach negative infinity. So from that maximum value of 5, your graph goes down from that value. So in interval notation, we're going from the smallest value to the largest value. Well, the smallest value would be negative infinity. But that's not an included point because you can't actually locate negative infinity on a graph. It's continuous, so we put a round bracket around it. And then the maximum value, 5, would be an actual included point, right? It's the point or the coordinate of the vertex, so we're placing a square bracket. Now, in set builder notation, for all values of y such that y would have to be less than or equal to 5. Now we're using less than or equal sign because 5 is an actual point on the graph. But from that point of 5 or the coordinate of 5, your graph is going to go downwards, so it's less than or equal to. Now that we've seen two examples of stating the range, remember that the domain is always x is all real numbers or from negative infinity to positive infinity when we're writing it in interval notation. So I want you to write the domain and range of f at x is equal to negative 3x squared plus 12x minus 8 in both of those notations. Now I understand that this is in standard form, but I want you to use your old math tricks and skills from the previous parts of this unit to get this into vertex form first, and then go ahead and state the domain and range. So what we want to figure out here essentially is the vertex, because whenever, again, you see the word maximum or minimum, that is referring to the vertex of the parabola. So if we're thinking about this like a graph, what's essentially happening here is that height, or where the ball starts at, is the y-intercept. And so because it opens downwards, we can expect the graph to go kind of something like this, okay, give or take. And that top of the hill here, that's going to be your max height. And in quadratic terms, again, that's the vertex. So what we're really looking for is this point over here. We want to figure out what the max height is, so the y coordinate of the vertex. And if we can figure out what the x coordinate is when it reaches that max height, then we'll be able to find the max height. So given that this is the quadratic formula in standard form here, that'll be our A, this will be the B, and this will be the C. And we're going to use the vertex formula, negative B over 2A, to get the x coordinate here. And we could complete the square, but it takes a little bit longer when we're dealing with decimals. So let's just use this formula over here. But if you do like to complete the square, then it is completely fine as well. So we're going to plug in everything here. And that gives us about 3.06 seconds for when it reaches that max height. So now what we're going to do is, by plugging in that x value here, which we said was 3.06 seconds, we can find out what that height is. And we can just take the original function, so h at 3.06, and wherever there's a t, we're just going to plug that value in. And this ends up being about 47.52 meters. So that's that part over here. And that would be the max height that this reaches. Now for part B, it says that the pitcher caught the ball at a height of 1.1 meters. How long was the ball in the air? Express your answer to the nearest tenth of a second. So what seems to happen here is it starts at 1.6 meters and then it falls eventually past that. And so what we're really asking for, if I'm going to do it in a different color here, is if that's 1.6, let's say that this part over here, this would be the ground. So at 0, that's the ground. But 1.1 might be around here. And that's where the pitcher catches it. So what time would that be? What would this part be specifically over here, what's that x coordinate? So now what we're going to do is we're going to take this height value here and plug it into this over here. And then we're going to isolate for our t. Now, because we're dealing with decimals here, it is simpler to just go ahead and use the discriminant formula or the quadratic formula. So that's what we're going to do here to get the x values. This is going to leave us with two x values, one at negative 0.016 and the other at 6.139. Now, since x represents time, time cannot be negative, so it's not going to be this one. This is going to be the answer that we go with. So it reaches the height of 1.1 meters, or the picture catches it at 6.139 seconds. Now, what this really is a vertex question. And the reason why we know that it's a vertex question is because it uses the word maximize. And whenever we have a maximum or a minimum that is being asked, we know that it has to do with the vertex. Now, if it's maximum, that means that your parabola is going to open down. And so imagine here that I have, let's say, profits. If this is profits, and it goes like this here, what I'd be looking for is this maximum revenue, right? Profits or revenue, I could just write R here, and that would be the max revenue. And what we're trying to find is what's that x value, okay, or the x coordinate of that maximum, so I could figure out how much I need to charge per week. So we'll put x as the charge per week. Now, for this problem here, you got two factors that are going to contribute to your total revenue or your profits, right? So if I think about R as in revenue, well, that's going to be a product of the, you could say, number of rented apartments. And then it's going to be also a product of the how much rent you charge per week. So I'm going to write amount charged per week. And so whenever we have a function which is the product of something, so in this case the revenue is the product of the amount of rented apartments multiplied by how much you're charging per week, then we know that we have to use the factored form of the quadratic, because that's the only formula where you have something times something. What I mean by that is that's the only formula where it's f at x is equal to, and then it's a, and then we could say x minus s and x minus t, right? This here means multiply. So one part of this problem could be the number of rented apartments. And then the other factor could be the amount per week. And so whenever your function is the product of two things, you know you should use the factored form. So when I'm substituting this in here, the first factor, which is the number of rented apartments, well, you have 80, that is the maximum capacity. And then let's say if you keep losing apartments, n can be the number of apartments. So 80 apartments minus how many you're losing if we increase that rent. And then the other factor is going to be the amount per week. Now, when I write the amount per week here, remember that it starts off at a flat rate of $200, and then you're adding 20 per week. And that's going to be per apartment, so plus $20 per apartment, where n is the number of apartments. And so this is the factored version of the quadratic that we're going to work with. Now, because we want the vertex, we're actually going to get this into standard form, and then from the standard form, convert to vertex form. Now, how do you get this to standard form? Well, you can use your distributive property in order to do that. Now that we have this quadratic equation in standard form, the negative 20n squared, well, that would be the A, the 1400 is the B, and then the 16,000 is the C. And so from standard form to vertex form, you could complete the square, but you could also, and it's probably a lot more efficient to do it this way, you can use the quadratic formula, or I should say the vertex formula of x is equal to negative b over 2a, and that'll give you the x coordinate of the vertex. And so we'll just plug it in as follows. And this would be 35 here. And so to get what that actual max amount is, that 35 corresponds to this value on the vertex. Then we can just plug in the question, though, is asking how much should you charge per week to maximize. So per week, it's 200 plus 20n. That would be the $900 per week in order to maximize the revenue.